Okay, so we were discussing network theorems, and we discussed substitution theorem in our previous video, and in this video we will see how nice, how useful substitution theorem can be, and we can derive or prove very useful theorems like Thevenin's theorem, using substitution theorem. So in this video we will do that. So in this video we will derive Thevenin's theorem, we will derive using substitution theorem. But before that, let me just recapitulate what Thevenin theorem says. The Thevenin theorem says that if I have a network, very complicated it can be, although I'm not going to draw a super complicated one now, maybe something like this. Or you can draw your own circuit as complicated as you like. Okay, so it says, the Thevenin theorem says that in this circuit, if I am interested to find the current only in a particular branch, maybe this one, so okay, so this one, this impedance I will call as ZL. L sometimes means load impedance, doesn't matter, for now it's just a name, and we are interested only to find the current through this, which is IL. Thevenin theorem says that it is possible to replace the rest of the circuit. Okay, so the rest of the circuit with a single voltage source in series with an impedance, and if these terminals I call them as AB, then here AB I call them, and I connect the ZL, which is outside this part, this box, as before. Thevenin's theorem says that for any complicated circuit, as complicated as it could be, if I'm only interested to find the current in this branch, I can replace the entire circuit with just a voltage source and an impedance in series with that. And this voltage source we call it VTH, TH for Thevenin, and ZTH, this impedance, again Thevenin impedance. And then if I compute the current IL here, and I compute the current here in this circuit, that will also be IL. So that's what Thevenin's theorem says. But the question is, what is the value of VTH and ZTH? Otherwise, my theorem is incomplete. Now, Thevenin theorem says that VTH is nothing but the V open circuit, V across AB, across these two terminals. I'm calling them as AB. So the voltage that appears when no load is connected, that means when this is open, these two terminals are open, not connected to each other at all, okay, then the voltage that appears here that is open circuit voltage, that should be the value of this VTH. And what should be ZTH? It is the impedance as seen from terminal or port AB with all sources deactivated. What does that mean? Okay, by deactivating sources, it means in the original circuit I have to replace all the voltage sources with their internal impedances, which ideally is 0. For this ideal voltage source, so this internal impedance will be 0. So I replace it with a short circuit, this branch, and then here the impedance, this remains as it is, this one as it is, this one as it is, and this current source I have to replace it with its internal impedance. And for current source, ideal current source, it's infinite, so I keep it as open. Okay, and then I measure the impedance between these two terminals A and B. Okay, so what is the impedance between these two terminals? Or in other words, if I apply a voltage, some voltage, let me call it V, what will be the current flowing through this? If that is I, then I call this impedance ZTH is equal to V by I. Okay, so that impedance, or you can find that impedance by simplifying this network of this passive network of impedances. That means these two in series and this one in parallel, simplified, that will be ZTH. Okay, so if I use that ZTH here and VTH, which is the open circuit voltage, then these two circuits are equivalent in a sense that if I connect same ZL outside, I'll get same IL. That's Thevenin's theorem. Okay, now it's time for the proof, because you probably know this Thevenin theorem from your first year's course, but this second year course should have something new, should have something more interesting. So in first year you only knew the theorem, but now you must know why it is true. Otherwise, why should you believe in it? Okay, so this now here goes the proof. Okay, so we'll use substitution theorem, and what we will do, we will substitute this impedance ZL with a current source. So let me draw. So let me first draw this box, this dotted box, black box. Whatever is there inside, I do not care. It's retained unaltered, unchanged, and the A and B terminals coming out. And then here I had ZL, right? Now instead of ZL, I put a current source, okay, like this. Okay, let me also draw the original circuit for reference. So that's ZL, IL was flowing through it, A and B, okay, and I go from here to here using substitution with current source. Okay, so according to the substitution theorem, I should choose the value of this current source equal to IL, which was the current in the original circuit. Right? Okay. Now let's ask the question, what was the voltage in the original circuit across A and B. Okay, so here in the original circuit across A and B, it was IL ZL. right? Since substitution theorem says that in the substituted circuit the solution should remain same, that means the voltage across A and B here as well should remain equal to IL ZL, right? Okay. But anyway, one thing you might be thinking of this, that IL is unknown, right? So IL is unknown. That's what we want to find out. That's our target. Okay. Once we know IL, if we know IL, we do not need to apply Thevenin theorem anymore, because that's what is the goal. And then we do not even have to prove Thevenin's theorem if we know IL. Okay, that's true. So, but here we are replacing this impedance with a current which is equal to IL, but IL is unknown. Yes, once again, this is unknown. But assume that if we knew IL, so let this be just an algebraic variable like x, which is unknown, which we will solve now later. Okay, so if we knew this x, IL, so we could have done this substitution. You might be thinking of this. Okay. So what did we say? So we said if this was VAB in the original circuit, according to substitution theorem, this should also be VAB in the modified circuit. Okay. Now, how can we find VAB in this modified circuit? So we can find and this modified circuit, okay, inside this we have a set of current sources. So they are actually inside, like this one, and also they have this internal voltage sources. Okay, so they are there inside, right? I could have actually drawn it inside as well, no problem. But this is basically the remainder of the circuit other than this load. Okay, so they were there, and now this is the voltage across these two terminals, VAB. Now this this voltage is caused by this internal sources plus this new external source. That's what superposition theorem says. So now apply superposition. To find VAB. Okay. So you want to find VAB using superposition theorem. So what does superposition theorem says? It says that we have to first consider the internal sources like this, the internal current source and the internal voltage sources. So which are these actually? For this voltage source and this current sources. Okay, and remove this one. So this current source is removed, and when it is removed, its internal impedance being infinite, we keep it open. And plus another circuit where we short circuit this voltage source to deactivate. So we are deactivating the internal sources and open circuiting the current sources. Okay, so basically replacing current sources by infinite impedance and voltage source by zero impedance, and here I keep the external one on. So this is IL. Okay, so this is one circuit and this is another circuit. If I find VAB for this one and VAB for this one, so this is A, this is B, this is A, this is B, so VAB for this one, and if I add them, this VAB and this VAB, I will get the VAB here. That's substitution theorem. Sorry, that's superposition theorem, right? Now, what is VAB here? This is, by definition, is nothing but V open circuit, right? That is the voltage that appears across these two terminals when nothing connected externally, but these internal sources are present and active. So this VAB is VOC, by definition, open circuit voltage. And what will be this VAB? Now this VAB will be, by definition, it's easy, clearly it will be equal to this current times the internal impedance of this circuit. Now if the internal impedance, that's by definition is Z Thevenin or Z internal, whatever you call, let me use ZTH, okay, ZTH multiplied by this IL, that's the current which is flowing, that should be VAB. But I should have a -1 because current is flowing from here in this direction. So from B to inside, then to A. So that means B is at positive side and A is at negative side. But here we were using VAB, A with respect to B, that means that this was our convention, plus minus. So this is in the opposite sense, so that's why I take this minus. Right? So now what we have these two voltages which we have to add to get the actual VAB here. So we will then have VAB equal to this VOC open circuit plus this one, okay, due to minus, I take minus ZTH times IL, where IL is unknown. We do not know IL definitely. Okay. But VAB should be equal to IL ZL because that's what it was here. So that means should be equal to IL ZL. Once again, IL is the unknown. But now what we will do from this constant, this equation, we will take IL on one side and solve for it to get the unknown. Let me just continue my maths from here onwards here. So here I have VOC minus Z Thevenin IL is equal to IL ZL. Right, now let me take IL in one side, so then I will have IL times ZL plus ZTH, okay, is equal to VOC, that's open circuit voltage, and ZTH is by definition, as I said, is the internal impedance as seen from these two terminals. Or in other words, as we are saying here, say if we pass a current I, then if the voltage that appears is V, then we call this V by I as ZTH. Okay, cool. So that's what we have now. So IL is the unknown. We write it as this. And this is Thevenin's theorem. That's what Thevenin's theorem says, right? So that's Thevenin's theorem. So it says that we can replace this with a VTH, voltage source and a current source ZTH, and then that means, that is same as saying this current IL will be equal to definitely VTH by ZTH plus ZL. That's Thevenin's theorem, and VTH is nothing but open circuit voltage, VOC. OC for open circuit. So that's what we have proved. And this we have done using substitution theorem. Okay? Cool. Now let us do it very quickly. Norton's theorem from substitution theorem. I do apologize for my bad handwriting. Okay, so we'll now do a derivation of Norton's theorem using substitution theorem. We'll do it very quickly for a practice. Okay. Suppose once again I have a network and it has two external terminals in which a load ZL is connected, okay, and it has a lot of internal current and voltage sources, and I'm interested to find the current IL in this branch. Okay. To get Thevenin's theorem, we substituted this branch with a current source. Similarly or reciprocally, to get Norton's theorem, we will substitute this with a voltage source. So this is equivalent to this network with internal current sources, circle with an arrow, internal voltage sources, plus minus and circle, and then here outside we replace this with a voltage source VL, I call it, and the value of VL I choose it to be ILZL. Okay, so that's the voltage which was during the original circuit. It's here. Okay. Now once again, IL is the unknown. That's what we want to find out. So IL is the unknown. Okay. Okay. Now. Okay. Now. Let's consider this current. This current is IL. Okay. That's what it should be according to substitution theorem. If I substitute this with this ZL with VL, which is equal to ILZL, then substitution theorem says that the circuit remains unaltered. So this current should be IL. It should remain IL. Okay. Now let's ask this question. What is the value of IL here? Okay. Now this IL we can think is contributed by the internal sources plus this external source. So we will use superposition and decompose this circuit into two parts. One has only internal sources and one has the only the external source VL. So this will be equivalent to this, with the internal ones but the external one will be deactivated. But this is a voltage source, so by deactivating we mean to short circuit it. Okay, this circuit plus I draw the shunt network. Now I deactivate the internal current source by making it open and deactivate the voltage source by making it short, which is internal. But now I need this one to be present. I forgot a very important thing, to put the plus minus sign. Okay, what should that be? According to substitution theorem, current flowing from top to bottom here. So this side should be plus and this side should be minus according to the direction of chosen direction of current. So this is plus, this is minus. So this is plus, this is minus, and the value here is VL, right? Okay. Now the question is, what is the current here? By definition, this current by definition, if it is I, this I is equal to the short circuit current, right? The current that flows when this terminal is shorted with internal impedances, internal sources active. That's what is by definition, that's what we call it to be short circuit current. I mean, that's its name, right? That's by definition, by name it is short circuit current. And plus, what will this current be? Okay, so if the internal impedance of this network is ZTH, then when this voltage VL is applied, then what should be the current flowing here? This current I, what should be I? So I should be nothing but VL by ZTH. Again, by definition, ZTH is the internal impedance. So if I apply this voltage source, the current will definitely be voltage divided by the impedance. But yeah, we should have a minus sign here because this is plus and this is minus for voltage source, but my chosen direction for current is from left to right, so I should have this minus. Okay. Now that, what does this mean? This current IL is sum of these two currents according to superposition theorem. So I can write that IL is nothing but ISC, this one plus this one, which is minus VL by ZTH, right? So IL is this. Okay, cool. Now, what is VL? VL is, I mean, ILZL. That's how I substitute it. So I put that value, so I have ISC, SC for short circuit, minus this is ILZL divided by ZTH. So let me take IL on one side, so then I have IL of 1 plus ZL by ZTH is equal to ISC, which implies that IL is equal to ISC multiplied by ZTH and divided by, this will be ZL plus ZTH, right? So this is what we get by applying substitution from here to here, and then superposition theorem, and then we solve for the unknown current IL. This is what we should have. Okay, now see, this is, if you remember what Norton's theorem is, this is Norton's theorem. Why? Because Norton's theorem says that this part of the circuit, this internal part, can be replaced with a current source in parallel with the internal impedance of this circuit as seen from these two terminals. Okay, so that's internal impedance Z Thevenin, you can also call it Z Norton, doesn't matter, this is the internal impedance, and this here we have ZL. That's what Norton's theorem says. Okay, so that means what will be IL according to Norton's theorem? IL will be, and yeah, before that, what is the value of this current source according to Norton's theorem? Norton's theorem says that this current source should be equal to ISC, which is the short circuit current. That is the current which will flow when I short circuit these two terminals. If I just join them, then that current is ISC. So this is ISC, and then if I apply current divider, so this ISC is divided between this ZTH and ZL. So the fraction that goes to ZL will be ISC multiplied by ZTH, the other resistance, divided by the sum of the two impedances, and this is IL, that's current divider, nothing but current divider. Okay, so this is current divider, right? So if we apply Norton's theorem, current divider, this is what we get. And if we apply substitution theorem, this is the same thing what we get. So Norton's theorem is true.